The Great Pyramid of Giza contains approximately 2.3 million individual stone blocks, with the largest elements weighing upwards of 60 tons. Building it represents an extreme engineering challenge, defined by raw, unforgiving mass. The project faced an absolute temporal limit, the reign of the pharaoh Khufu. While estimates vary slightly, archaeological consensus suggests a window of approximately 20 to 27 years. Distributing 2.3 million blocks across a 20-year schedule reveals the mandatory throughput rate. The builders had to extract, transport, and place one multi-ton block roughly every 60 seconds, 12 hours a day, for 2 decades. This thesis represents the traditional approach to solving the construction math. Most researchers rely on demographic modeling, calculating worker housing, grain rations, and the total labor force required to haul stone. However, the 1 block per minute requirement creates a spatial bottleneck. Adding more human labor eventually hits a point of diminishing returns, as tens of thousands of workers cannot physically fit onto the narrow working surface without halting the flow of material. The construction of the Great Pyramid poses a problem of kinetics. Maintaining continuous volume at this scale requires a mechanical solution that prioritizes material flow. Historically, 3 transport models are proposed: the mile-long linear ramp, the internal core ramp, and the exterior spiral ramp. To understand why these models struggle to meet the kinetic limit, we have to look at the mechanics of moving a multi-ton payload up a winding path. This top-down schematic maps the critical failure point of the spiral ramp model, the 90-degree corner. Because large pulling teams operate in a straight line, they cannot drag a payload cleanly around a sharp angle. At each corner, the block must be stalled and manually rotated. The forward velocity drops to 0. In a single file system, this creates an immediate ripple effect. A block paused at a corner halts the entire kilometer-long chain of workers behind it, making a 1 block per minute pace physically impossible to sustain. In a 2025 paper published in NPJ Heritage Science, Egyptologist Simon Schuring argues that external ramps must be rejected because they inherently violate the kinetic speed limit. If external structures cannot support a continuous flow of stone, the transportation engine must have been integrated directly into the interior architecture of the monument. This is the Grand Gallery. While often viewed as a ritualistic corridor, its architecture suggests it functioned as a high-capacity transit shaft for moving weight. The Grand Gallery and the ascending passage share a uniform, highly specific incline that cuts through the pyramid's core. Rising at a precise 26.5-degree angle creates a 1/2 geometric ratio. In vector mechanics, this partitions gravity's force on a sliding weight. A counterweight on this slope generates roughly 45% of its gravitational force in tension on a connecting rope. This tension matches the exact requirement for a 2-to-1 mechanical advantage pulley lifting a payload vertically. The uniform 26.5-degree slope appears to be a rigidly calculated requirement, optimized to interact with a 2-gear pulley engine. The Grand Gallery leads into the antechamber, a space traditionally dismissed by early explorers like Petrie for its seemingly crude and substandard masonry. The west wall contains 3 anomalous half-round indentations. Archaeologists have identified these as the support positions for massive wooden logs. Schuring's model reinterprets this room as a pulley hub. Ropes are folded over these static logs and routed down to a payload block, creating a Gear 2 system. This doubles the required rope length, but halves the force needed to lift the block. Deep rope guidance grooves in the south wall extend a full meter above the wooden logs. This height is unnecessary for a static door system, but it is required for controlling ropes in a vertical hoisting shaft. The granite leaf likely served as a mechanical lock, securing ropes while heavy counterweights inside the Grand Gallery were reset for the next lift. The antechamber shows the characteristics of a wear-tested industrial tool, a vertical pulley shaft used to hoist 60-ton beams found in the King's Chamber. To find physical proof of this machine in operation, we have to look directly beneath the Grand Gallery in the horizontal passage. The masonry here is uniquely symmetrical and features non-standard cross-shaped joints, a layout where 4 stone corners meet perfectly, violating standard rules of staggered stacking. These joints are the expected result of blocks being pulled up the active gallery ramp and extracted laterally into the walls, preventing the builders from using a traditional staggered pattern. This diagram maps the alignment between these cross-shaped joints and a series of vertical grooves cut into the Grand Gallery walls, 10 meters above. The horizontal and vertical spacing of these features matches the lateral extraction points required for a hoist operating within the gallery. This non-standard masonry represents the fossilized trace of a moving industrial machine, physically recorded in the stone structure of the pyramid. The exterior layers of the pyramid also carry signatures of the lifting process. By analyzing the horizontal courses of the face, we can see the output of the peripheral pulley systems. When Flinders Petrie measured these courses, he found that the thickness of the blocks does not thin out uniformly toward the summit. Instead, the course heights oscillate in decaying sections, where block thickness drops in distinct, repeating cycles as the elevation rises. This jagged pattern matches the physics of a peripheral pulley system. Once lifted, crews exert lateral force to pull the hanging mass sideways onto the surface. As the surface climbs and the rope shortens, the lateral force required to extract the block increases. To compensate for this increasing force, builders had to use progressively thinner, lighter blocks at the top of each pulley phase, creating the decaying course heights Petrie recorded. Under specific lighting conditions, the stone faces of the Great Pyramid reveal a subtle vertical furrow slicing down the center. This furrow appears to be the vertical scar left by the primary exterior hoist paths, which were kept open until the final stages of construction. This model synthesizes the internal counterweight core and the stepped peripheral pulleys into a single cohesive engine. These systems operate simultaneously. The exterior pulleys handle the high-volume mantle blocks, while the internal core hoists the massive structural elements of the King's Chamber. In 2017, muon radiography discovered a big void above the Grand Gallery. Showering's model predicts this housed a secondary internal pulley system. This presents a testable hypothesis. The new void should possess the exact same 26.5-degree slope as the galleries below. By focusing on kinematic constraints rather than raw manpower, the Great Pyramid emerges as a product of highly optimized, energy-efficient mechanical engineering, a monument designed to maintain a relentless pace of construction.